Hello, my name is Gerhard and I'm a data scientist at SAS and lecturer at business schools and universities. I have a passion for statistics and data science, and in this webinar I'm sharing data science case studies that I experienced from my professional life. Today we're going to take a look at how you can use multivariate statistics to get more insight into your forecast errors. This data science case study is taken from a larger collection of data science case studies, as you can see here on the screen. Today, we take a look at the explanation of forecast errors and deviations in forecasting. I also present case studies on employee retention. I present simulation case studies, text analytics case studies, and case studies where you can let your data talk and use unsupervised machine learning techniques to find out more about your customers and your analysis subjects. However, today we go and take a look into that. Our today's topic is taking a look how you can use multivariate statistics to better explain forecast errors and deviations. And we're also going to answer the question whether the demand planners do a good job when they manually overwrite the statistical forecasts that we have. The paper that I'm presenting here has already been successfully presented at SAS Global Forum back in 2018, and you will find a download link for this video where you can download the presentation and the SAS Global Forum paper, which shows an extensive collection of information, SAS code, and considerations on this topic. In this presentation, we take the business question of how we can explain the forecast error and use advanced analytic methods to get more insight and to have answers for business actions and business results in order to find out when are forecast errors sometimes high and when are forecast errors sometimes low. We also speak a little bit on data preparation considerations and how you can prepare the data in order to perform this analysis. There is more information in the paper that you can download for this presentation that also talks more on code snippets, on regression procedures in SAS, or on relevant examples how you can visualize the data that you're seeing here. Let's take a look on the business background of our case study. We're talking here about an international retail and manufacturing company who is doing demand forecasting on a monthly basis. The demand forecasts are generated from time series forecasting models for products who have a time history of 16 months or longer, and for forecasts for products who have a shorter time history, machine learning models with regression techniques like Poisson regression or gradient boosting are used. The company now wants to understand the deviation in forecast quality. For some products, the deviation is quite high, for others it's quite low, and they would like to get more insight what are triggers and what are drivers for a higher or a lower forecast error. So the business question of our case study is that the company would like to better understand the distribution of the forecast error. They will also find out which factors influence the forecast error, whether it's high or whether it's low. They would also like to find out where it makes sense for the data scientists to invest more time in order to improve the forecast quality, and also to see which combinations of forecasts of products being launched in a certain time frame in a certain product group might always have a larger forecast error. And finally, also the question whether the manual overrides of the demand planners really improve the forecast quality. So the basic idea of our example looks as follows. We have a product, for example, the item 1673, which has a forecast generated by the analytical model looks like follows. And we now see the actual values. We see that in some months we are a little bit more far away from the true value, and in other months we are closer to the actual value with our forecast. And we would now like to study whether features of the forecast and the product have an influence whether the forecast error is larger or whether it's lower. Let's take a look on the available data and the data preparation processes for our case study. We see that we use statistical forecast data. This is the data that are generated by our analytical forecasting system and where the forecast for each product and each month are stored in a database. We also have the information available about the manual overrides when the demand planners finally override the statistical forecast by a value which they think is more appropriate. These data sources are combined, and believe me, also they need to be data quality checked, even if they come out from quite well-maintained systems, because you might always find situations where you have a statistical forecast but not the final committed value. You might find situations where you have manual overrides but no statistical forecast. Make always sure that you take a data quality look on the data that you receive in order to get a better impression about the completeness and the consistency and the timely alignment of your data. Here we use the features like which forecast model has been used. Is it a Riemann model? Is it an exponential smoothing model? Is it a regression model? For how many months in the future the forecast has been created? What is the target year? And also very important, because of seasonal cycles, what is the target calendar month for which the forecast is generated? We also use features about the product itself. In which product group is the product designed that we are forecasting? What is the price? What is the calendar month when the product has been launched? And also very important, what is the product age, meaning what is the available data history that we have for this product for our modeling. Again, this data is being combined together and calculated as some derived variables. Also, the deviation between the actual value and the statistical forecast in order to judge whether we have a large deviation or we only have a small deviation. You see that I'm using the MAPE here for the analysis, and I'm well aware that there are a couple of reasons why you should not use the MAPE. On the one hand side, the MAPE is asymmetric, whereas a perfect fit results in a MAPE of 0. Deviations can go to extremely large values on the other side. If the observed demand is 0, the MAPE formula doesn't work, it gives a division by 0. And another thing is that a forecast of 0 always gives a MAPE of 100. So it might be that you train your forecasting or your machine learning models that learn this fact and better forecast 0 for all time points, as with that way they can limit the MAPE. We are aware about these problems and these disadvantages of the MAPE. However, the MAPE is still very widely used in business forecasting because it's easy to interpret. It is in many companies like a standard which can be easily communicated to the demand planners and to management, and it is very often used as a status quo to compare the companies also with other companies in the industry. So beside all the disadvantages of the MAPE, we are still using it here in this case study. Let's now have a look on the overall distribution of the forecast errors. When we take a look at this distribution here in the chart and on the descriptive statistics, we see that on average we have an absolute percentage error of 85. If we take a look on the quantiles, we see that the median is around 40. So this means that 50% of our product forecasts are lower than 40 and the other half is higher than 40. The first quartile is 18, meaning that 25% of our product forecasts are lower than 18, the others are higher than that value. You have to bear in mind that some of these forecast errors are quite high because this company has a lot of new products of items that are sold in the fashion industry where no or only a very short data history is available, and thus might lead to higher forecast errors. We now would like to study in a little bit more detail potential variables that affect the size of the forecast error. First, we take a look on product age. A longer product age means that more historic data is available, meaning a longer data history is available. So we see over time that the forecast error decreases with increasing product age, with increasing data history. We also see very clearly that we have in the first 12 months a higher value, in the next 2 years a lower value, and then starting with the third year another lower level. So this means additional years of data history decreases our forecast error, especially in the first 2 or in the first 3 years. It's also important to recognize that also descriptive methods can help you to give you insight and to better understand the forecast error, especially over time. Let's take a look at the following graph. We see here that the forecast error for short-term products, meaning products that only have a short time history, are usually higher. So these are the models which of our products which are generated with the short models, with the machine learning models, compared to those in the long section which are using time series method. So the more time history we have, the more data history, the better we can model, the lower our forecast errors are. We also see that over time, over the years 2010, 2011, some models got discontinued and other models started to do the forecasting for certain products. We also see that some models might exhibit a larger forecast error compared to other models, not because they are worse forecast models, but maybe they are very good to forecast specific, very difficult products to forecast, and thus exhibit a larger forecast error because they are applied in more complicated cases. Let's now take a look on the results from univariate linear regression models, where we study the influence of different input variables that we have available for each forecast on the forecast error. We see here a ranked list from the univariate models. What are the best or the most influential variables on the forecast error? We see that the different forecast models have a very strong influence as we see them here. So we see for the short models, the forecast error is usually higher compared to the long-term forecast models, which can consume a longer time series from the model. We also already studied that product age has quite an influence, where we see the downward trend as we saw it on the example before. We also know that the product group has quite a difference, that there are product groups which are much harder to forecast compared to others which are easier to forecast, where the demand is not as volatile compared to others. We also know that there are some launch months which are harder to predict. For example, close before summer, it seems that this is harder to predict compared to other months in the summer or in the autumn area, which also has an influence on the forecast error, and also other variables as we see them here. What is the target year? Is there a trend over time? Or is there a particular calendar month where it's harder to generate a forecast compared to others. Let's now compare the selection of the variables from the univariate model, which we have just seen, with the multivariate linear regression model. What I've done now is I have entered all the 8 variables into the model in order to see what are the most important variables in a multivariate model. We see that variable model is entered first. We might have assumed this because it's also the most important variable in the univariate model. And we see that the adjusted R square is 5.4%. We see also that longer forecast models have a lower forecast error, shorter forecast models have a higher forecast error. Now, however, the next important variable is target calendar month. So we see, compared to the univariate model, this variable overtook many of the other variables because these other variables, for example, product age, have content which have already implicitly been told by the model variable long or short. So the next most important variable in a multivariate model is target calendar month. For which calendar month is the forecast created? Is it harder to predict the early spring season, the autumn season, or the Christmas season? This is the next most important variable, and we see it seems that it's quite hard to predict the variables, the forecast that are generated at the end of the half year and in June or in December. And we also see the other variables like product group. We see some product group are quite nice to forecast, others are harder to forecast. We know that the target year has an influence. We see this it has a positive effect, meaning that over the years our forecasts are getting a little bit more imprecise. We also see product age with a negative forecast. This is also what we studied before, where the forecast values are going down if we have a longer data history, and other variables with a lower effect, for example, like the price index or the launch month and others. As we now have this regression model, which explained us the content and the relationships of our available data on the output, we can now also use this regression model to calculate predictions. We can now, for example, take if we launch a new product, what is the expected MAPE if we launch a certain product? So for example, let's take the product SAS Global Forum t-shirt, which is in a certain product group being launched in July. The target month for which is the forecast should be created is May. We have certain product age. We use a certain model to forecast this, and we have the model logic which we have just created from our regression model. If we now combine this new data with our model which we just created, we can perform a scoring and receive the information that for this product with a forecast for the next 4 months, we have to expect a MAPE of 65. This already gives some indication in order to judge if we have certain product groups, if we have certain combinations, are these scenarios which are harder to forecast or which are easier to forecast. There are also possibilities to study the linear regression results which we just generated visually. So let's take a look particularly on the product age variable. We see that when we perform univariate analysis, so when we only use the product age variable, we see that we have a downward trend in a linear way as we already had it in the univariate model. If we, however, enter product age as one of many other variables, like product group, model type, lead time, target calendar month, and so on, we can study in a more detailed way that product age has not quite a linear downward trend, but we see that we have in the first year a larger deviation, starting then with the second year deviation like this, and after the second year then we have quite a linear downward trend. So combining analysis and variables in multivariate models and displaying them in special deviation scenarios by showing product age to the deviation, we get much more insight compared to the linear model only, to the univariate model only. Let's now finally come to the discussion whether demand planners really improve their forecast quality with their manual overrides. Let's take a look at the graph that we have here on the right. I created here a line and band chart where the line shows the median of forecast differences between the statistical forecast and the manual forecast, which is created by the demand planner. And the band shows the first and the third quartile of this variable. Let's now take a look at the scenarios. If the demand planner increases the forecast, we see the scenarios on that side. If it decreases the forecast, we see the scenarios on that side. And on the vertical axis, we can see whether they do good, whether they decrease the forecast error, or whether they increase the forecast error. So we find out that we see here a section where demand planners apply some changes, where they add very small changes to the data. However, they do not have any positive effect. They simply increase the forecast error. Only if they do larger changes, they have a larger and also positive effect. So we see with some increases, here we see that the median really goes down. And this finding corresponds with the work of Paul Goodwin, where he says, if they do small changes, demand planners very often waste their time. Only if they do larger changes, they invest more thought, they must be more sure. There, they really do good when they change the forecast, because they have a specific reason to say there might be a certain promotion in a certain region which the model couldn't capture in the past, and I have a good reason to override them. So it's a good advice to leave out these small changes from your forecasting process. They are very often just a waste of time and do not add any benefit, only when you perform larger forecast overrides where the demand planner really has to put more thoughts into that. You have seen now analysis where I used univariate and multivariate analysis to study the forecast error in more details. Possible next steps in the analysis is to create decision trees which allows better to discover segments of products with a higher and with a lower forecast error, which are easier to communicate to the business users. It's also a good project which we have started in parallel now to perform forecast value add analysis. This is a specific regression model to find out whether the manual override of the demand planner by increasing or by decreasing the forecast error really adds benefit, and in order to generate advice whether the demand planner should be allowed to do so or whether he should not be allowed to do so based on the expected added value when doing the override. So my takeaways from this presentation here are that the application of analytical methods provide you relevant insight and help you make better decisions, we were able to find out that we see in a visual way and in a descriptive way reasons why sometimes the forecast is higher and why it is sometimes lower, and what variables have a strong effect to trigger high or low forecast errors and which variables have a less effect, have a smaller effect. Using our multivariate regression model provided us a much more comprehensive picture than just the descriptive and the univariate analysis, and it allowed us to perform deeper analysis, also to forecast and to study what is the expected forecast error for a certain model, and then maybe find out specifically which forecasts are higher or lower compared to its expected forecast value. And all these analyses have been performed with the SAS platform and have created this output. In this case study, we have seen that analytics and data science is here to help you. It allows you to get a clearer, more objective picture based on your data in order to better judge about your topic and your outcome. In our case, we studied the forecast error to see what variables are here important, and the multivariate regression model just gave us the answers instead of us having to ask each question individually in order to get a finding. So we made our data talk to us. They told us that model and target calendar month are the top most important variables. And we received our findings automatically and allowed us to do this analysis on a regular basis in order to see the outcome of our forecasting process. This example and more are covered in my book Applying Data Science, and I explained in very much detail in order how to perform this and how to use the data. Thanks for watching. I hope you enjoyed the content that I present here, and I look forward welcoming you to more topics which I publish on the DACH YouTube channel on these topics. And I'm also happy if you read my blogs on LinkedIn or if you follow me on Twitter or GitHub and take a look at the content that I'm providing. Again, today we took a look at this case study explaining forecast errors and deviations, and in future webinars I will also cover other topics, for example like text analytics, letting the data talk to you, or survival analysis for headcount, analysis of employee data. Thanks a lot for listening, and I look forward to talking to you again.